Kaumudibikash Goswami from LAM. He's a scientist working on the Quest satellite project in the Quick Lab of RRI. And today he'll tell us about the current developments in Quest. Quest is quantum experiments in satellite technology.
Hello everyone, my name is Kaumudibikash Goswami. I am working as a scientist C who joined in February 2022 this year and working in quantum experiments with satellite technology, in short Quest project. So this project is in collaboration between RRI and ISRO, and the overall aim of this project is to ensure a long distance quantum communication. Particularly, we are aiming for a long distance QKT entanglement based QKT protocol, where we are going to communicate between two optical ground stations via satellite, low Earth orbit satellite. So let me introduce the team. So this project is being led by Professor Urvashi Sinha, and we have an active international collaboration with Professor Barry Sanders. And these are the current and past members who have played a pivotal role in this project. So due to time constraint, I'll be I'll pass through these slides. So we all know, like, classical cryptographic protocol ensures security. However, there exists like a quantum algorithm that can break the hardness of classical cryptographic protocols. And we have quantum key distribution, where Alice and Bob, two communicating parties, share n-bit string, and they can communicate by encoding this like shared key string on the image, and Bob can decrypt this encrypted image by applying the same key. And there are two different classes of QKD. One is prepare and measurement based QKD, whose security is guaranteed by Heisenberg's uncertainty principle. So we have demonstrated a prototype of B92 protocol, a particular class of like prepare and measurement based protocol, in our lab. And this has been the first QKD protocol in India. And the second one is entanglement-based QKD, whose security is governed by monogamy of quantum entanglement. And we have also successfully demonstrated an entanglement-based QKD protocol. So one question we can ask, why do we care about satellite-based QKD? Why don't we use a long transatlantic optical fiber? Well, so one major challenge that the information carrier, that is single photons, will face through optical fiber is they will face a huge transmission loss, and that will drastically affect the secret key rate. And the other question is, why not do ground-to-ground optical free space optical communication? Well, we can do that, but it will limit our free space distance. That is, at some point, receiver will get out of line of sight. So in these cases, satellite-based quantum communication plays a pivotal role, and it will it allows us to have low loss and long distance quantum communication. This particular example is a downlink-based quantum communication protocol. The Chinese Micius satellite has successfully demonstrated such downlink-based protocol. So in a downlink-based protocol, the entangled photon source is in the satellite, and the measurement stations are at the disposal of the ground stations. So these are works that shows successful implementation of downlink-based downlink-based satellite QKT protocol. However, in our Quest project, we are focusing on an alternative approach where we place the source at the ground station and place one of the detectors at the satellite. So this is what we call uplink-based QKT protocol. And why uplink? So first of all, so because the entangled photon source is at the disposal of the experimentalists, they will have more flexibility to play with the source. That is, at some point, if we want to replace it with a brighter source, experimentalists will have the freedom to do that. And also, suppose like we we want to incorporate some exotic quantum state in the protocol, so we can we can incorporate quantum memory where we have uploaded that exotic quantum state, and we can use it for the communication purpose after satellite launch. So with that brief introduction, I will talk about the milestones that we have achieved. So we have achieved in lab B92 QKD protocol, where we are doing prepare and measurement based QKD. And we have also developed a software package to simulate the performance of QKD, which is also known as QKD Sim. Professor Barry Sanders tomorrow will give a more detailed description of this QKD Sim software package. And then we moved on to generate entanglement-based QKD protocol, which is also called BBM92 protocol. We have incorporated 50-meter, like we have translated this BBM92 protocol over a 50-meter long free space channel. And next, I'll be talking briefly about the moving receiver platform, where one of the detector modules will undergo translation, and we need to apply pointing acquisition and tracking to monitor that translation. So first, I'm going to talk about B92 protocol. So these are the members who have been involved in this experiment. So brief idea of B92 protocol. Here the sender, that is Alice, encodes the bit 0 in diagonally polarized photon and bit 1 in vertically polarized photon. On the other hand, the receiver Bob measures the incoming photon in either horizontal polarization basis or anti-diagonal polarization basis. So the idea is, whenever Bob detects a horizontally polarized photon, he knows it for sure that it cannot come from vertically polarized photon. So horizontally polarized horizontal detection will ensure that bit 0 has been transmitted. And the same logic can be applied to anti-diagonal detection. So with that, theoretically, we can secure, like Alice and Bob can secure a key string, which is which should perfectly match. However, in practice, this doesn't happen, and as shown by these red flip bits, there is possibility that some of the bits are not matched. So the question is how much error we can allow. It has been shown that if we restrict the Q bar, that is the quantum bit error rate, below 4.8% for B92 protocol, we can always apply some error correction algorithm to error correction protocol to distill an error-free key string. So with that, I'll describe the experimental setup. So here we are impinging a 405 nanometer pump beam on a in a PPKTB crystal. The generated two daughter photons so one of the daughter photons are used for heralding process, which I will describe shortly after this slide. And the other generated daughter photons is used to randomly encode the key string. That is, she can either encode in diagonal polarization basis or vertical polarization basis. So Bob, on the other hand, after receiving the single photons, can randomly measure in the relevant basis, that is horizontal and anti-diagonal basis. And note that there could be two possible attacks in such setup. One is photon number splitting attack, where a malicious party, Eve, siphon off some of the photons to acquire some information. So this photon number splitting attack is alleviated by using heralded single photon heralded detection. So that is like in heralding process, Alice and Bob performs a coincidence measurement between this detector and two of the Bob's detector. Now, whenever there is photon siphoned off to a third party, that is Eve, then this coincidence will drop, and the communicating parties can abort the QKD session. And the other possible attack is when Eve tries to influence the random choice of measurement and preparation. So this we ensure by incorporating a passive random number generator, that is beam splitter. So this ensures that like with equal probability, we are either preparing or measuring the single photons. So before delving deeper into the result, I will briefly describe that we have also in this project we have also prepared a simulation software called QKD-SIM that incorporates various experimental imperfections and can give us an assessment of our QKD protocol. So imperfections like detector, like timing, zeta, dark ground are all incorporated in this modular based Python package. And tomorrow, Professor Barry Sanders will present a detailed description of this QKD-SIM package. However, I'll move on to the result, where you can see that our experimental result has an excellent agreement with simulated predictions. So we have key rate, that is what is the rate of in 1 second how long of a key we are generating, and Q bar. So you can see we have achieved 51 kilohertz key rate and a Q bar of 4.79, which is information theoretically secure, that is below 4.8%. Also, we have a balanced key symmetry, that is there are equal number of zeros and ones in the generated key bit. And this protocol is competitive, globally competitive, as you can see as you can see in this comparison. So, I'm happy to share that our work, this work has got a lot of highlights from popular media to industry blogs, and most importantly, it has been selected as one of the 20 major success stories by DST. And on that happy note, we started implementing the next milestone, that is an entanglement-based BBM92 protocol. So here, these were the active member. I joined in February this year, 2022. So before that, first to implement a BBM92 protocol, first we need to ensure a good entangled photon source. So in January 2020, we achieved a very good performance in this single photon source. That is, the measure of concurrence was around 99%, and purity was 99.4%. And then I joined, and concurrence is 91%. Okay, this is not the full story. So as you can see, this data was taken in January 2020. So after that, due to lockdown, the source statistics dropped. And when I joined, so this is this was the concurrence, 67%. At some point, it dropped to 0. So then Saurav and I started working on it, and we achieved a 91% concurrence in our source. So why not go further? Why not aim for 99%? So we decided to move on to the next milestone, that is to implement the BBM92 protocol. And on a brighter side, it has been shown that even with 91% concurrence, we achieved robust error-free implementation of BBM92 protocol. So this is the brief setup, the setup of BBM92 protocol. And due to time constraint, I'll not describe in detail, but I'm happy to answer questions. So basically, the generated single photons are routed to two different detector modules, Alice's module and Bob's module, through a 2-meter long optical fiber. So conventionally, Alice and Bob measures in either horizontal vertical polarization basis or diagonal anti-diagonal polarization basis. And whenever the polarization they look at the same polarization basis, then they can establish a secure key string. So note that in this BBM92 protocol, we have to maintain the Q bar, that is bit error rate, below 11% to achieve information theoretic security. Now, we not only restrict ourselves in a successful implementation of BBM92 protocol, we address a practical challenge. So note that for a satellite-based QKD protocol, we need an optical ground station surrounded by a friendly atmosphere. And my colleague Satyaranjan is tirelessly working on characterizing atmospheric turbulence at different geographical locations. However, in practice, however small that turbulence is, it will affect the signal. And we know that polarization is a very robust degree of freedom, but for 600 kilometers, it will undergo some polarization scrambling. So the question is, can we devise a method that mitigates this atmospheric, the effect of polarization scrambling in a friendly lab environment? The answer is yes. To do that, we perform a quantum state tomography at the output. A quantum state tomography is a method to characterize the like various parameters of the received entangled state, and based on the tomographically generated entangled state, we choose the optimal measurement basis that Bob can perform. So one of the so we keep Alice's measurement basis as conventional, that is either HV or DA, and we have some optimal measurement basis for Bob that can nullify the effect of atmospheric turbulence. Note that this is so the conventional approach to mitigate such polarization fluctuation is to incorporate quantum process tomography as well as active feedback. Here we are not doing quantum process tomography, we are performing quantum state tomography, and we are not using any active feedback based mechanism. So to assess the performance of our modified protocol, we intentionally vary the fidelity of our quantum state with the ideal singlet state from 10% to 94%. As you can see, when we measure in conventional basis, that is both parties are measuring in HV and DA basis, the Q bar gets worse with lower fidelity. However, with our modified protocol, we can achieve information theoretically secure Q bar of 10.5%, irrespective of any polarization scrambling. So we reported this work in this paper, and it is under peer review process. And to discuss to give a brief description of our performance of the BBM network protocol, we have achieved 50 kilohertz key rate and a Q bar of 10.5%, which is below information theoretically secure threshold, that is 11%, and we have achieved a balanced key symmetry of 50 is to 49. So on that note, we moved on to implement a 50-meter long free space link, where one of the detector modules, that is Bob's module, is transferred to a distant building 50 meters away from from our source, and these are the active members who participated in this implementation. So these are the two buildings that is 50 meters apart, and the Bob module is transferred to the nearby cabin, and so we use a refractive optics based mechanism to route the single photons to the distant cabin, and this is the overall description of the optical setup. And as you can see, we achieved information theoretically secure Q bar of 11% as in February 2021 with 1.6 kilohertz, and this month we have improved the statistics. We have achieved even lower Q bar with higher key rate, and this is the first QKD protocol demonstrated over an atmospheric channel. Note that there has been an alternative attempt to implement such long distance free space BBM QKD protocol. That attempt was to reflect Bob's single photon over a mirror and getting it back to the same lab. That is overall the photon traveled overall 200 meters. However, the effective distance between Alice and Bob was around 2 meters. So it is really not really not like the free space link that we are looking for in an actual satellite-based scenario. And the other point is, in such scenario, like it overcomes a major challenge where we have to synchronize two detectors. Note that in realistic satellite-based QKD protocol, the two detectors will not be at the same location. So we need some global clock to achieve the time reference and create the coincidence peaks. And so this we have done in this incorporated in this free space link, and my colleague Prabhakaran and Saurabh has worked on development of this synchronization protocol. So after implementation of 50-meter long 50-meter long free space at free space BBM92 protocol, we have moved on to another like protocol, which is moving receiver platform. So where we have added another layer of complexity, where so where one of the measurement stations were further apart from the source, as well as it's undergoing some translation. So we need a robust pointing acquisition and tracking method to monitor that translation. So Prabhakaran and Sujata has been working on this, and as of now we are able to demonstrate a proof of principle demonstration of moving vehicle, moving receiver demonstration, where we mimic the translation of Bob's movement using a gimbal mirror, and basically this translation will account for the real life scenario of satellite movements. And so once the translation has happened, the imperfections in the beam path is corrected by simultaneous active feedback mechanism by movement of these two gimbal mirrors. So this has been achieved in an in-lab environment, and our next step would be to scale it up in a outside lab environment, where we will actually implement the BBM92 protocol on a moving receiver, on translating moving receiver, and we'll incorporate pointing acquisition and tracking system to nullify any effect due to the movement of the detector module. So here are the future milestones. So we are like we will demonstrate the BBM92 protocol on a realistic moving receiver demonstration, and then all our ground-based like demonstration, optical demonstration will be performed, and we will be working on miniaturized space-compatible payloads. For example, our colleague Bella is working on space-compatible detectors. And once this development has been done, we will collaborate with ISRO to ship the payload to actual satellite, and hopefully it will have the success of the experiment. And I will end this talk by a gentle reminder that tomorrow Professor Barry Sanders will present a wonderful talk on his works at RRI. And I'll remind you again that he will present this, he will discuss in detail on this QKD-SIM protocol, QKD-SIM software package. So please, like everyone is invited to come to this talk. And I will end this talk with acknowledgement and special acknowledgement to Dr. Sita for helpful discussions on satellite technology. And thanks to the other relevant lab members. Thank you.
You mentioned these two technique. One is, I think you called uplink, and the other is downlink. But in the uplink case, because you're sending photons through the atmosphere to a satellite, and there are fluctuations in the refractive index in the atmosphere itself because of pressure variations, won't the pointing stability be a huge problem, or is that
Well,
Are there ways of taking care of
this is the trade-off like we have to like face. So like uplink-based QKT protocol will have to face much more atmospheric loss compared to downlink-based protocol. However, there are other advantages of uplink-based protocols. So like the way to compensate for this atmospheric loss is to really look for some like proper optical ground station that has friendly atmospheric environment. Also, we have developed this like polarization scrambling mitigation technique, so that due to like even due to like excess loss, like we can mitigate this any polarization scrambling due to like greater atmosphere. But yes.
because when there are refractive index variations, then your beam is not going along a straight line, right?
Yeah, that will be one of the major challenges to do that. And I think
So in your earlier slide, you had a zeros and ones, the balancing ratio you were talking about, 49
yes,
point
key
something.
symmetry.
So what is the requirement for a packet length of what is traditionally required for the
So ideally, we want balanced key symmetry. So
50-50, right?
50-50.
So this is going to restrict your packet length.
Yes. So like ideally, like we could achieve, like the way we achieve it is by post processing. We like maximize the entropy by getting rid of some of the key bits to achieve the like maximal entropy.
And what is the target speed bit rate?
Well, so far we have achieved 56 kilohertz. So in lab, and target as you mean by like what will be at the satellite level. So so far the reported is like in the range of bit per second. So like because of atmospheric loss. So so we want to ensure as much key rate as possible in lab environment. So our type 2 crystal, with our type 2 crystal, we are able to generate 56 kilohertz, and it is possible to achieve like much more like higher key rate with a different type of crystal, like type 0 crystal.
So, Prabhu, just to add to that point, the aim of this, sort of long distance thing is not to have a very high key rate, but to have keys which we can use for secure communication. So, indeed, at the moment, the entire community is not focused on increasing the bit rate. We know it will be, some bits per second. So, that calculation we have done. So, we are happy with that because we'll be measuring over a few months and generating a long key for whatever the requirement is. Once this proof of principle is done, and that is why, of course, Kaumudi was highlighting the uplink part, because if we actually come up with the brighter source that he's hinting at, which we are working on ourselves, then of course that bitrate thing also goes up automatically. We can replace it. So long as our optics, the wavelength doesn't change, the satellite optics doesn't change. So we can do such replacements on ground with the kind of thing we are attempting. So it's 800 nanometer. Yeah. 400 is the pump. Yeah, you want to.
No, I was asking what decides your wavelength for communication? Where is the constraint coming from?
Well, actually, 810 nanometer is so. For example, for now we are using this 810 nanometer. However, it is also possible to go for non-degenerate down conversion, where one of the photons is in 775 and the other one is 842. So far the calculations we have done based on telescope requirements, it takes into account of this particular wavelength, and it achieves requirements of all the requirements on divergence angle and all these things are based on this 810 nanometer.
So Kaumudi, maybe the question is why? So that is because it has a good window. So we have actually done the analysis for, as a function of wavelength, what is the kind of transmittance we get as a function of wavelength. So if you see that graph, which is not with him right now, 800 and 1550 are both good actually, windows, okay? But then we don't want to do 1550 because we are doing uplink. So the detectors at 1550 for single photons have 15 to 20% efficiency. So we will really be sub-bits per second if we attempt 1550. So we want to be at 800, where the detector technology is much better developed. So that is the trade-off really. So we are choosing 800 because of course we know how to generate them, and also it has a good pass. So there are these windows where you have good pass. Atmospheric transmittance is good. There are like 3 or 4 such windows. Yeah, yeah. So that is the analysis which led to this being a natural choice.
Okay, let's thank Kaumudi and all the speakers.